Welcome, everyone, those that are very familiar to us and also those who are visiting us for the first time. This is the second lecture of the spring series. The spring series is actually our 11th symposium series, and this is the theme of this series is on water and quantum biomolecules. And a very warm welcome today to Ali Hassanali, who's coming to us from Trieste in Italy. And without further ado, I'm going to hand over to Dr. Betony Adams, who has been working with the Guy Foundation for many years, running our scientific communications, and is also postdoctoral, doing postdoctoral research in quantum biology at Stellenbosch University. So with that, Betony, if you'd like to share your presentation and introduce our speaker for today.
Thank you so much, Geoffrey. It gives me great pleasure to introduce Dr. Ali Hassanali for the second session of the spring series on water. Ali Hassanali was born in Tanzania and spent most of his childhood in Nairobi, Kenya. After obtaining a BSc and MSc in mathematics at Purdue University, in his own words, he saw the light of physical chemistry working with Sherwin Singer at the Ohio State University on atomistic simulations of water at organic and inorganic interfaces. He was a postdoctoral fellow at ETH Zurich and the University of Lugano, working with Michel Paranello. He is now senior research scientist in the condensed matter and statistical physics at the Abdus Salam International Center for Theoretical Physics in Trieste, Italy. Ali leads an international group interested in theory and atomistic modeling of water, including topics such as solvation, hydrophobicity, ions, confinement, and more recently, optical properties of hydrogen bond networks. His research has been funded by several grants, including a Horizon 2020 EU grant on artificial photosynthesis and an ERC Consolidator grant. Ali is also active in science capacity development at the ICTP in the Global South. This makes him an ideal speaker for a series that is preoccupied with the interesting physical behavior of water, but a series that is also interested in why certain scientific subjects are advanced while others fall behind or are viewed with suspicion. And throughout his talk, Ali will touch upon the apparent contentious issues and claims that the scientific study of water elicits. In our first session, Dr. Philip Kurian did an excellent job at introducing the physics of water and why water is such a fascinating compound in the context of biology. Dr. Hassanali will expand on this interesting physics by looking in more detail at the specific behavior of water at interfaces. What do we mean by interfacial water? Very simply, an interface describes some sort of boundary between two different regimes of behavior. In physics, this interface could separate phases of matter, such as liquid and solid. Ali will build on his research into the use of soap bubbles for artificial photosynthesis and the interesting properties, such as big electric fields in ordered water, that are associated with these artificial membrane interfaces. And finally, Ali will give some insight into how model membranes, such as soap bubbles, might give some insight into how water behaves around the charged membranes, mitochondrial and cellular membranes, for instance, that are so integral to biological functioning. He will also touch on the importance and open questions regarding light-matter interactions, where water plays a crucial role. I think it's a fascinating and relevant subject, and I'm looking forward to hearing what he has to say. So without further ado, let me hand over to Dr. Hassanali for his presentation. Thank you.
So thanks very much to the Guy Foundation for having me here. In particular, I want to also acknowledge Philip, who I've worked with in the past, for bringing me into the circle. And so what I want to do today is tell you a few stories and perspectives on sort of my own interaction and work on the physics of water, with a focus on trying to understand dielectric properties, so charge layering near hydrophobic interfaces, and their implications on the interactions with light, which is what I will do towards the end of my lecture. And so just to sort of start with the big picture and calibrate you where I'm coming from. So I'm based in Trieste in Italy. I work in the condensed matter group at the Abdus Salam International Center for Theoretical Physics. And just to kind of give you what the big picture of what my group is interested in, I lead an atomistic simulation group interested in studying aqueous systems, so watery systems, both in the bulk, at interfaces, under confinement. And we use a wide variety of techniques ranging from electronic structure, molecular dynamics, and now more recently also unsupervised and supervised machine learning to try to understand the properties of water at interfaces. And one thing I just wanted to highlight here, which is why I started with showing the picture here of Abdus Salam, is that one of the focuses of my interest in my group is also doing science without borders. And I bring this up because I think in the times that we live in at the moment, I really believe that science can be a really powerful and universal language that brings people together from all over the world, from different backgrounds. And this is what we try to do at the ICTP. And I'd be happy to talk about this at length during the Q&A. And so just to kind of pitch the big picture, one of the main focuses of questions that I've been interested in since the beginning of my career is whether water plays a role as an active participant in physical, chemical, biological processes, or is it a background solvent? And I've put throughout my talk some interesting references where I think are useful for people who are interested in getting into this field. And this one here was by Misha Bon and co-workers, where they show kind of a picture of water near a mineral surface. This, could be calcium carbonate, silica. It could be a metal in the middle, or it could be water near a biomembrane. And one of the big questions that continues to be in the field is essentially, how does an interface perturb and change the structural properties of water, the dynamical properties of water, and the dielectric properties of water? And one of the kind of sort of aspects related to understanding that question is, how exactly large is the interfacial region? So if you have a biomembrane or a metal, what length scale does the interface perturb, or the surface that you're interested in perturb the structural, dynamical, and dielectric properties? And is that length scale going to be the same when you probe structure versus dielectrics? Okay, so that's been kind of an essential theme of or question that I've been asking over the last decade. And I just want to give you one example of these, which kind of illustrates not only a scientific point, but also a bit of a philosophical point on the power of labels. And so this was about 2 decades ago, over 2 decades ago. The late Ahmed Zewail, who got the Nobel Prize in Chemistry for his discovery of femtosecond spectroscopy, came up with this idea that if you had a biological system like a protein or a membrane, there would be this region of water around it that would be perturbed dynamically. And so you would have a region of water that was immobilized because of strong interactions of water near the protein. And this got under the umbrella of the label biological water. And so this, for almost a decade and a half, both experimentalists and theoreticians, computer simulators, were trying to understand, well, what is the meaning of biological water? And I find this a very interesting article by Pavel Youngworth, and the cartoon here is a bit tongue-in-cheek. It's basically a fishing rod pulling out a fish from the water, and the fish says, if you put me back into the salty water, I will reveal the secrets of my function to you. And one of the things that emerged from the study of biological water is that essentially water near proteins is no more biological than water near any other type of mineral or electron surface. And biological function was not only rooted in the properties of water, but actually how water changes the thermodynamics and dynamics of the substance that we're looking at. In this case, it was, for example, proteins, but you can think of it also in terms of DNA. And just sort of to illustrate this point, you could ask the question, is water near silica? So silica is silicon dioxide. You see it it's basically the main substance that makes sand in contact with water. And if you were to zoom in, as I'm showing you on the right slide, to a silica water interface, for many decades, there was a large community of people thinking about electrical double layers. So how does water near a silica surface change relative to the bulk? And this led to the construction of labels like things like a stern layer, which was considered to be a stagnant layer of water. And then eventually what came out of it was that, water near these types of interfaces is different, and it is slowed down just like it is near a protein, but that the magnitude of that slowing down is no larger than a factor of 10 on average, okay? So this is just to by way of introduction to tell you that the field of the study of the physics and the chemistry of water has a bit been challenged by historical constructions of labels, but then not rooted or founded on microscopic molecular theory. And so what I've been doing, and many people in the community of aqueous systems have been trying is to try to really dissect this using theoretical experimental techniques. And what I'm going to try to do over the course of my talk is to give you a glimpse at some of these types of issues. So as Betony already kind of alluded to, the study of aqueous interfaces or watery systems has been a very contentious playground. And people always get very passionate in the water community about is water special, and how different is it compared to other liquids. And so one of the hot topics in the field, which is still a topic of a lot of debate, is, are water interfaces charged? So if you take a biomembrane, you take an electrode, you take a surface of silica, is the water near it neutral, or does it have some charge associated? And where does that charge come from? And so one of the kind of questions that emerged, almost over a decade ago was, is the surface of the air-water interface acidic, basic, or neutral? So this is kind of interesting because, the notion of pH, so the concentration of protons in solution is a thermodynamic quantity. We know how to define it in the bulk, but is it a relevant thing if you ask what is the pH at an interface? And so there was a community of people, and there still is, who believe that interfaces attract protons or hydroxide ions. Another one, and this is something that we contributed to, was that basically aqueous interfaces, so for example, water in contact with air or water in contact with oil, has a negative charge, but not because of the presence of ions like protons or hydroxide ions, but it has a charge because of electronic charge transfer that occurs between the water molecules and the oil surface, in the case of oil. And this is, again, also in part of a bigger sort of observation, which is that many experiments have shown that when you put water in contact with a hydrophobic surface, it seems like there's some contact electrification taking place. And this is an area called triboelectric effects. Again, where exactly these things come from is also very controversial and contentious, because one of the challenges, experimentally at least, is when you're dealing with water, you don't know how pure your water sample is. So do you see something in water that is coming from something explicit or intrinsic to the water itself, or is there something inside the water? Is it an impurity? Is it dirt? And this has made it challenging, but of course then very interesting to develop experimental and theoretical techniques to try to understand this. Related to this charging of interfaces, another kind of related aspect is this observation that if you have an aqueous interface, like water in contact with oil or water in contact with air, there is an apparent enhancement in catalysis. So chemical reactions are observed to speed up. And so this has been led over the last 10 years by Richard Zer's group at Stanford on the left, where they took aqueous microdroplets and spontaneously electrosprayed them, found the generation of hydrogen peroxide. And although this has been hotly debated on by another group in Saudi Arabia, Himanshu Mishra, who've shown that actually the enhanced reactivity in these droplets doesn't come from the droplet or the interface itself, but comes from impurities like ozone in the atmosphere. And so you do an experiment in one part of the world with a certain amount of ozone, and you do another, that changes the yield of the hydrogen peroxide. So is the reactivity really coming from the interface? And one of the things that has been advocated as being as a key player in driving chemistry of these aqueous microdroplets is the presence of large electric fields at the interface. And so this is something that I'm going to try to kind of point to through some of the things that we've discovered in my group. So I know some of you are interested and are thinking about mitochondria. I'm not an expert myself, so I'm going to put myself out there, and we can certainly discuss this. I saw this very interesting paper of a coarse-grained inspired model to build an atomistic model for a mitochondria. And if you start to think about water interfaces in the context of mitochondria, you can sort of begin to ask, well, how much does the structure, dynamics, and dielectric properties change near these interfaces? What are the roles of these electric fields created by water? And can one change the equilibria associated with the ionization of water in this interface? And of course, these are extremely challenging because now you have much more richer chemistry and heterogeneity in the membranes, and this is something that I will get to later on in my talk. So I'm going to start by an example of let's say, a more fundamental driven research, which was funded by the EU on artificial photosynthesis. And so this was a collaboration with the partners here shown in the picture. And the idea was basically, can we use soap bubbles to do artificial photosynthesis? And I'm going to show you this example because I think it's a really nice demonstration of the ping pong between experiment and theory and how we got to a rather deep understanding of some of the questions that I've posed to you earlier on in my talk. So just to frame the context, we all know what photosynthesis is. Nature leaves do this very efficiently. They take in light, combine it with CO2 and water, and use that to generate oxygen and sugars. And so the idea behind this soap bubble project was, can we use a soap bubble to kind of mimic a leaf? And can we design the right chemistry on the surface of the soap bubble that would allow us to do the types of processes efficiently that you would do in photosynthesis? And so without going into a lot of detail here, sort of the picture that we imagined doing when we wrote this proposal was essentially you have two bubbles that come together, and in each of these bubbles you have carbon dioxide. They form an interface like the one that you're seeing in the middle here. And by designing the chemistry correct on one interface and another, so you allow for water oxidation and CO2 reduction to happen appropriately on either side, you might be able to generate, to do photosynthesis. Okay, so that was the proof of concept that we were aiming for. And so ICTP, so my group, was tasked with trying to develop a fundamental understanding of these thin film of the soap film. So the soap film, if you zoom in, is basically this layer of water in the middle, and then you've got these sort of surfactant or soapy molecules that sort of serve as the boundary of the two interfaces. And so we were tasked with trying to develop atomistic models of the soap films and help and guide and aid the interpretation of the various experiments. Okay, so one of the big challenges when you want to design a good atomistic model is you need to be able to validate it. And so basically, the experimentalists were using a soap, a surfactant called C12E6. I'm not a chemist, so I don't even know how to pronounce this molecule, but basically it is a molecule that has a hydrophobic tail that hates water, doesn't like water, and it has a hydrophilic tail made up of oxygens that attract water. Okay, and so that's why this soap forms a membrane when you put it in contact with water and air. And so the first thing we did was to try to do molecular dynamics simulations of this surfactant. And the first thing we tried to do was to validate whether our model correctly reproduces things like the surface tension. Okay, so our experimental collaborators, Techless, this is actually a company that does a lot of measurements of emulsions and forms and soaps. They measure the surface tension, so these are the cohesive forces that exist between the water molecules at the surface, at the air-water interface. And so when you start with an air-water interface without any surfactant, you have a surface tension of 72. That's this number here. And then as you add these soapy molecules, that surface tension drops until it gets fully covered to a number of 32. Okay, so it drops by 40 millinewtons per meter. So we can go ahead and try to ask, how does our model that we have do? So this is done with molecular dynamics. And don't worry about these details, but basically we can estimate the differences in the tangential and the normal pressure tensor in our simulations, and that yields us a value of about 38 millinewtons per meter. So it's in reasonably good agreement with the experiments, which allows us then to start to make some predictions about what else is going on in our model. So one of the first things that we learned in this whole exercise is that if you just take in this simple system of C12E6, which is a really simple surfactant, the line between hydrophobicity and hydrophilicity is very blurry. And what I mean by that is essentially that we like to think about hydrophilic objects as the things that like water, hydrophobic that don't. But when you think about the thermal fluctuations and the conformational changes that can happen of this molecule in its true surfactant environment, essentially you have a lot of water that can penetrate into the oily hydrophobic regions. So what we thought was hydrophobic is actually not as hydrophobic as one would classically think that it is. Okay, so that was, let's say, one of the first things that we observed in our simulation. And so we wanted to know whether this was an artifact of our model or whether it was a manifestation of something real going on. And so we went back to our experimental collaborators. And so this was done with Dr. Herb Bakker. So Herb Bakker leads a vibrational spectroscopy group in Amalfi in the Netherlands. And so this vibrational spectroscopy, it's called some frequency vibrational spectroscopy, is a nonlinear type of spectroscopy that basically probes the vibrational modes of water at interfaces. So you get a signal when water is at an interface, so in a non-centrosymmetric environment, but when the water is in the bulk, when it's centrosymmetric, you don't get any signal. And so what this technique allows you to do spectroscopically is it measures how the water molecules are hydrogen bonded at the interface, and it also measures how the water molecules are oriented. And you can do this type of measurement both at the bare air-water interface, like in the image shown here, but also when you start to add the surfactant. And so in the situation like this, where I'm showing you these water molecules trapped inside the surfactant, you can also measure their orientation. Okay, so they do their experiments, and I don't want to get into the details of this, but I want to tell you what it actually reports. And so what you see here is a vibrational spectrum of water, and that's the solid black here. This is just bare water with air, essentially. And this thing on the y-axis has a sign. So it has a negative and a positive value. And the sign of this quantity tells you about the orientations of the water molecules. And so what this plot is telling you is that when you go from the bare air-water interface and when you add these soapy molecules, there's a huge shift in the spectra. So you can see that the signal kind of moves to the left, and the signal moving to the left means that you're getting stronger hydrogen bonds. And the other thing that's changing is that you see that what was a negative sign here in the bare air-water interface becomes positive. And so adding the soap, adding the surfactant changes the orientations of the water molecule. Okay, so that's what this experiment is telling us. So now we can go back to our simulations and see, do we get the same result? And so you can focus on the figure on the left, which basically shows the projection of the orientations of the water dipoles in the case where you have just the air-water interface compared to the case where you have the surfactant. And what you see is that there are these two peaks in both cases, but adding the surfactant flips the orientation. Okay, so the fact that there's a change in the sign in this spectroscopic measurement is really manifested at the molecular scale in the change of the orientations of the water molecules, which is seen also in our models. So now we can ask, well, what is the implication of having these flipped water dipoles? That's number one. And number two, if you look carefully on the x-axis, we're talking about a length scale of about 3 nanometers. So on a length scale of about 3 nanometers, we have some interesting orientational polarization. So what we can do is we can take our oriented dipoles and measure or compute a charge density. And so we do this first for our air-water interface. And the picture on the right is how you should imagine the water molecules oriented. So the top layer has, protons pointing to the air. The bottom layer, they're slightly pointing to the bulk. And this kind of distribution leads to an angstrom or several angstrom thin layer of charged layers of water that's coming from the oriented dipoles. Okay? So that's at the air-water interface. So now let's do it for the surfactant soap film interface. And what you see here is the charge density that I've plotted here for the total, which is in black. So that's a charge density that's coming from the oriented dipoles of the water, but then also a charge density coming from the soap, because the soap, the surfactant, also has its own electronic charge. So it's obviously more complicated. But basically, the total charge density at the interface is coming from a complicated mix of the charge density or the orientational dipoles of the water and also the surfactant at the interface. And this basically leads to a layer of about 3 nanometers where you have these charged layers. Okay, so now if you have charged layers, you can go back and ask, well, if I invoke Gauss's law, this must imply that there is an electric field or a surface potential in some sense. And so we can extract the electric fields that are built by these underlying charge densities that come from, again, the solvent, the water, and the soap. And what you find is that in both systems, so on the system in the picture on the right, this is the electric field at just the air-water interface. right at the surface, you have a huge field. And this field is about 1 volt per nanometer. At the surfactant water interface, there's also a huge field. So it's about 1 volt per nanometer. But of course, it is spread and covers a length scale that is longer than what we had at the air-water interface. Okay, so the take-home message here is that at both these interfaces, you do have the existence of a large field. That large field, of course, emanates or comes from the underlying charge density or oriented waters and the oriented surfactants. Okay, that was a theoretical prediction, and I generally tend to be very doubtful about my theoretical predictions. So I always want to go back to experimentalists. And so we went back to experimentalists at University of Torino, and Silvia Dante uses something called Kelvin probe measurements. And so they come with a vibrating electrode. They put the soap film on a platform, and they can measure basically the surface potential that's created due to the presence of this capacitor in some sense. And so the measurement that they get from their experiment is that they have a surface potential of 0.7 volts. We can, of course, take our electric field, the ones that I showed you earlier on. I can back infer a surface potential, and the number that I get is 0.53 volts. Okay, so, I'm satisfied that my model works reasonably well at getting close to the experimental, let's say, measurement. So now you can do something else, which is you can say, if I have a surface potential of 0.53 volts, and I have the surfactant dipoles sitting in this, let's say, capacitor, what is the effective dielectric constant that you would expect the soap film to be? And so we know what the surface potential is, we know what the dipole is, we know what the surface charge is, which is the sigma A, and so I can infer an effective dielectric constant. And so the effective dielectric constant that we propose exists in this soap film is about 4. So that's really small, right? And so basically what we're arguing is that in this particular case, this soap film leads to a very low dielectric medium. And obviously this has important implications on electrostatic interactions, for example, and the length scale over which these electrostatic interactions occur. Okay, so just to summarize a bit this first part of my talk, the narrative here is that even in this simple soap film, we have a large electric field at the interface with a very low dielectric environment. But now let's go back to the question I asked at the beginning, which is, for some of you who are thinking about mitochondria, and you're asking, well, how do I take these results and what would be the implication in this context, in the membranes in these contexts? And so one of the challenges, of course, is that the interfaces in the case of the mitochondria have a lot of spatial and chemical heterogeneity. So how does spatial and chemical heterogeneity change the underlying charge densities and electric fields? Okay, and so that's likely going to create a lot more heterogeneity. And it will likely lead to creation of regions where the electric fields are much larger and others that are much smaller. So one way to try to explore this idea is to turn to a new set of experiments, which we asked our experimental collaborators to do, which is to say, rather than just using the molecule in the bottom, that was the original soap, that's a neutral soap, let's do an experiment with mixed surfactants. So one of the popular surfactants or soap molecules is the sodium dodecyl sulfate. So it is a charged surfactant, so it has a negative charge. And let's mix the two together and let's see what happens. So I won't get into the experimental results. What I want to show you are some of the theoretical underpinnings of some of the things that we learned. And so basically what we want to do is ask, what is the free energy or the work the reversible work required to take this DS minus, so this is this negatively charged surfactant, and bring it to the surface of water. So this is without any surfactant there. And then let's repeat the analysis. Let's ask the same question. Let's ask, what is the free energy required to take this negatively charged DS minus surfactant and bring it to a film, a soap film that is decorated with all these C12E6 neutral surfactants? How does it change? And basically, the message I want to convey to you is that the thermodynamic driving forces, when you start to add a mix of interactions, can change the whole story. And so on the left, what we've shown is that the driving force for the DS minus to come to the surface is entropically driven by the nominally hydrophobic effect. On the other hand, if you bring the DS minus to this decorated mixed surfactant, it becomes enthalpically driven. And so basically the driving force for the thermodynamics completely changes. And so the driving forces for things under spatial chemical heterogeneity, I think remains kind of an interesting and an open question. And so just to kind of close and complete this part of the discussion, I'm just showing you here a decomposition of the total contribution of the interaction energy of bringing in this negatively charged DS minus ion to the interface decorated with C12E6. So this is this thing on the right. And what I want you to take away from this is that this minus 40, these are in units of thermal energy, so minus 40 kBT, comes from canceling, compensating contributions of many, 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 many different things. Water-water interactions, sodium-water interactions, sodium surfactant interactions, and all of these together, combined together, lead to large compensating numbers, can lead to the number of 40. And so water is important in these contexts, but so are all the other things in the solvent. Okay, and I think maybe the intellectual challenge is how to dissect and understand all these different contributions. Okay, so moving to another aspect, which I tried to motivate earlier on in my talk, is something that we've been interested in my group, is how does water reactivity change under confinement or at interfaces? And one of the main reactions in chemistry of water is the reaction that I'm showing you here, which is essentially the object that controls pH, right? So in all our freshman chemistry or high school chemistry, we all learned about this equilibrium. And funnily enough, even though this is the thing that causes pH, the underlying microscopic mechanisms by which this occurs still remain poorly understood. So we were interested in asking, how does this change when you go to confinement, when you're in a cluster, when you're sandwiched between a thin membrane? And so what we did was we asked ourselves the following question: how does the pKw, or the free energy required to ionize water, change going from bulk to having a cluster? And so we took a bunch of clusters, 6 water molecules, 12, 20, an interface like the ones that you saw before for the air-water interface. And what I want to show you here, or the take-home message here, is basically that the free energy to ionize water remains surprisingly the same, or remains remarkably bulk-like. And so these plots here I'm showing you are free energy versus an order parameter that tracks the dissociation of your water molecule. And it is only when you get to very small sizes of 6 water molecules that the water dissociation constant changes. Okay, so that was kind of an interesting surprise for us. What happens under confinement, right? So the confined system that we decided to think about was taking 2 graphene layers. Okay, and I take 2 graphene layers and I squeeze them and I create confined water. And it is known, it has been known for many, many decades, that many thermodynamic, dynamic, and dielectric properties change drastically under confinement. So what would that imply for the free energy of dissociation? And so if we do the same exercise, we ask, what is the free energy to dissociate water under confinement? Basically, it is only when you get to length scales of under 15 angstroms where you see a noticeable change in the free energy. And basically, it costs more energy to dissociate water as you put it under confinement. So it doesn't get easier, it actually gets harder. And the reason for this has to do with the fact that it's all rooted in what we think of as local solvation. So when you're creating these ions, so for example, the hydronium ion and the hydroxide, so hydronium, the proton, is the thing that lowers pH. The thing on the right raises the pH. When you go to confined environments, it is only when you get to extreme confinement that you change the local geometry and solvation. Beyond those length scales, or beyond the size of n equals 6, you essentially retain your local solvation. And so most of the thermodynamic work associated with creating these ions is essentially controlled by local geometrical effects. There's no, at least we don't find evidence for non-local or drastic effects on non-local effects on the free energy of dissociation. So again, going back to water dissociation in the context of mitochondria. And I think the question is, what is the extent of confinement in different regions of the mitochondria? Do they approach the length scale of less than 15 angstrom, where you would then begin to see really drastic changes in local structure? And then kind of a related point, which I would be happy to kind of discuss with the others here, is what is the role of pH in the functioning of the mitochondria? Okay, so in the last 5 to 10 minutes of my presentation, I want to tell you a bit about a very new and exciting, pun intended, area that we're looking at in my group, which is how exactly does UV light interact with water? And this is a really, let's say, loaded question with a bunch of loaded answers. And a big part of that is it has been very, very, very challenging experimentally to understand what is the origin of the UV absorption of water, because we don't really know what absorbs and at what energies. What photochemistry, if water absorbs UV photons, what is the kind of chemical reactions that happen upon electronic excitation? And this sort of ties a lot in with the question of what are the radiative and non-radiative mechanisms after water absorbs UV photons. And I just want to mention that these questions and these challenges are a bit tied to one of my earlier sort of starting points, which is in many experiments of water, one of the big controls and challenges is purity, sample purity. And small amounts of contaminants can drastically change observations, like things like optical spectroscopy. So on one side, these are a challenge from an experimental point of view, but on the other side, from the point of view of theory and modeling, this is really an interesting and a nice playground, because we exactly know what we put into our model, so we can really understand and try to see what's going on. And so one of the questions that we've been asking is, for example, in the context of this chemical reaction that controls pH, basically when you go from the left side to the right side, you are going from weaker hydrogen bonds to stronger hydrogen bonds, right? Because on the left, these are essentially dipole-dipole interactions. On the right, these are charge-charge, electrostatic, so stronger interactions. And So the question we've been asking is there a coupling between the hydrogen bond strength and optical properties, in particular in the UV region? And basically, the system that we've been trying to address this question on is basically ice. And the question is, can photoexcited ice emit visible photons? And the reason why we got to ice is because ice is, well, simpler from some points of view because you don't have to deal with thermal disorder. You have to deal with other challenges. But on the other side, there were these very interesting experiments in the 80s and 90s showing that when you UV irradiate ice for a certain amount of time, they were able to observe luminescence. So, so without getting into the kind of the too much into the physical aspects of the system, essentially, in everything that I showed you earlier on, the models that we use are all on the ground electronic state. And that's a great place to be because you don't have to worry about breaking something known as the Born-Oppenheimer approximation. Okay, so this approximation that the time scales of the electrons in the nuclei are very different, so you can separate them or adiabatically decouple them. When you're dealing with photoexcited processes like the one that I'm showing you in this sort of schema here, you excite something from A to B, it relaxes from B to C on an excited state, then you are going to break the Born-Oppenheimer approximation, and so you have to deal with more challenging theoretical aspects. But this is something that one has to do if you want to understand what happens on the excited state. So I won't get into the details, but I'm just going to give you a feeling of what we're finding when we do this in ice. So A represents the bottom of the ground state potential energy surface. This is hexagonal ice, okay, ice cube from your fridge or your freezer. You excite from A to B, that's about 9 eV. So the UV absorption, the band gap of ice is roughly at about 9 eV. So you have to dump in 9 eV to electronic excite from A to B. Using some excited state modeling, we relax from position B to C, and we basically find that the C to D energy transition is about 5 eV. So you've had a huge change of energy going from 9 eV all the way to 5 eV after photoexciting ice with this, far UV photon. That's number one. Number two, when you excite ice, the relaxation pathway from B to C leads to the creation of the hydronium ion, so the H3O plus that I told you earlier on about, and an OH looking like species. And this OH looking like species is actually a radical. Okay, so and essentially what's happening is when you excite the system and you're creating the configuration C down here on the excited state, you have a hydronium, an H3O plus, an OH radical, and the generation of an excess electron in the system. Okay, so this is it's a very complicated, a very rich kind of system. And when the system emits a visible photon going from C to D, the electron recombines with the OH radical, and you create H3O plus and OH radicals, OH minus species in the ground state. Okay, so one of our let's say hypothesis at the moment is that the visible luminescence that is being observed in those experiments is because of the creation of these species that then lead to recombination of the electron with the hydroxyl radical, and this ultimately leads to the creation of these hydronium and hydroxide, which we know in the ground state spontaneously form from thermal fluctuations. Here, there's now a path to create them through photoexcitation. So I wanted to kind of wrap up and close my talk with this kind of a question, and also why we chose ice. And so ice is a system where people have also observed and been interested in the role of quantum effects. And so I just want to tell you, well, what I know different people define what quantum effects are. And so when I talk about a quantum effect, I have two things in mind. Number one, it's the thermal de Broglie wavelength. And so the thermal de Broglie wavelength of a hydrogen atom is about 0.1 angstrom, okay, 0.1 to 0.2 angstrom. So this is kind of the uncertainty that the proton would experience because of quantum fluctuations. The other thing that I think about in the context of quantum effects is zero-point energy. So zero-point energy associated with the vibrational frequencies associated with the modes in the system that I'm studying at. And so in ice, the thermal de Broglie wavelength and the zero-point energy are sort of kind of coupled to each other. So the zero-point energy fluctuations, of course, affect the delocalization of the hydrogen, of the proton. And one of the things that well, we're trying to think about and try to understand is how would quantum effects in this system change the photophysical properties of this landscape that I'm showing you here. And so this is still an open question. We're trying to think of ways to tackle this, but it's still kind of an open question in the group. So I want to end with this slide and sort of try to again connect with what the relevance of this is in the context of mitochondria. So again, I'm not an expert on that. I did a bit of reading on this, and one of the things I found interesting was this observation that one can induce through blue light protein aggregation in the mitochondria. And one of the things that I think is very interesting that to ask and to wonder about is if you've got this structured, polarized, low dielectric water at an interface, if you've got light at different frequencies, maybe in the far UV, maybe in the near UV, interacting with the water, interacting with the protein, interacting with the hydrogen bonds in the protein as well, on top of the quantum effects that I showed you in confined systems. And that's kind of a question, is how confined they are. What would their effects be on biophysical processes? And I don't think there's an answer to this yet. And I don't think they are, I don't know of any kind of experiments that allow you to probe these. But the examples that I showed you today of model systems where you can really ping pong back and forth between theory and experiment, I think provide a very instructive way of being able to tackle these. And maybe one can do similar things for more complex systems. So I think my time is done. So I want to close and wrap up. Almost everything that I've showed you has been thanks to a huge collaboration of many talented students and postdocs over the years. In particular, I want to thank the ERC that has funded me through a consolidated grant, and the SOFIA, which was the project on the artificial photosynthesis. And I want to highlight sort of, besides the members that you saw earlier on in the artificial photosynthesis, 3 other experimentalists who have been working very closely on trying to use surface sensitive spectroscopies to really try to understand how water changes at interfaces. And with that, I'd like to thank you and be happy to enter into the Q&A.